Hello and welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving Leetcode problem 2416, sum of prefix scores of strings. Before we get into the video, you guys know the drill, like and comment, it helps me a ton with the YouTube algorithm. Literally put whatever you want in the comment section below, I don't care. Let's get into the question prompt. You are given an array of words of size n consisting of non-empty strings. We define the score of a word as the number of strings words of I such that word is a prefix of words of I. For example, if words equals A, AB, ABC, CAB, then the score of AB is 2 since AB is a prefix of both AB and ABC. Return an array answer of size n where answer of I is the sum of scores of every non-empty prefix of words of I. And do note that a string is considered a prefix of itself. Okay, we read the question prompt. Now let's look at a basic example. So let's start with our first string, ABC. What are the prefixes here? We have A, we have AB, and we have ABC, right? So in our words, how many strings have a prefix of A? Let's count them. So A, there are two strings, AB and ABC. So there's two that have a prefix of A. How many have a prefix of AB? Well, it's going to be ABC and AB. So that means that there's, again, two that have a prefix of AB. And then how many have a prefix of ABC? Well, it's just ABC. So for ABC, we only have a count of 1. So sum these up, we get 5, right? So in our solution at the 0th index, we're going to have 5. Okay, let's now move on to the next word. So we have AB, right? So AB has two prefixes, A and AB. So how many strings have, A? Well, we've done this before. It's going to be 2, right? So we have 2, and we've done the same for B already, and it's already 2. So we know that the sum here is going to be 4. So for the first index, it's going to be 4. Then we move on to the next string, BC. And what are the prefixes here? We have B and BC. So how many strings in our words here have a prefix of B? Well, it's going to be BC and B. So for B, it's going to be 2. And for BC, there's only one that starts with BC, and that is going to be, BC itself. So for this one, it's going to be 3, which means that at the next index is going to be 3. Then we get to B. So obviously B only has one prefix, and that is B itself. How many words start with B? That we already determined is 2. So our final solution here is going to be 2. So this is our final solution. It's going to be 4, 5, 3, 2. And this question is relatively simple when you do it this way, but unfortunately it's actually quite complicated to do it in code. And if you were to basically go through the process that we went through, it's actually quite inefficient, and you'd end up, even if you had some sort of memoization, you'd still have a lot of duplicates, and it would not be a very efficient solution. So what we're going to do, and I'll erase all of this in a moment and we'll go over the actual solution, but we're actually going to build a trie here. Because that way, given that we're working with prefixes, tries are basically the perfect data structure for that. So let's kind of think about on a broad level how we might implement our algorithm here. We're not going to go too much into the depths of the trie. We're just actually going to implement it into code because I think it's much easier than trying to draw out a trie here. So let's now erase all this and talk about the trie. So I told you that we want to build a trie. So let's think about what that trie may look like. Obviously, we always have the root of our trie, and then we want to build it out. So we obviously are going to go character by character. So we're going to go like there's an A character, and then you could have a B character, and then C. So that's going to be how you would do it for ABC. For AB, obviously A already exists, B already exists, so we don't have to do anything there. B, okay, that's a new prefix, so we would put B in there, and then from B you can go to C, and then we also have B on its own, which is already in there. So no problem. But obviously we have our trie now, but we want the counts. So all we need to do is when we insert a word, we actually want to update the count of every time we've seen the character. And essentially what we're going to do is we're going to have this count, And once we've built the trie for all of the words, all we need to do is now just count, get the counts for each of our words, right? And then that will be basically what we put at each index. So let's kind of go through this at a very basic level. So we have our root. So we get to A, and what are we going to do here? Well, we get to A, and what is the count that we've seen at A, right? It's just going to be 1, right? So we'll say the count is currently 1, and then we get to B, so the count here is currently 1 as well, and then we get to the C in ABC, and the count here is going to be 1, right? Relatively straightforward. So let's now go to the next word, so AB. So how many times have we seen A? Well, it's twice, B, twice, and then we're done there, right? And then we get to B on its own, so we're gonna insert BC, and we've seen it once, and we've also seen C once, once it's followed prefixed by a B, and then we're gonna insert the B, we've already seen it, so this becomes 2. So now essentially we have our, trie built with, each of the characters and the times that we've actually seen them. So what we want to do now is we simply want to count basically all the counts that we have. So for ABC, we're going to go into ABC, right? So we're going to go, okay, how many times have we seen a prefix of A? So we have 2 prefixes of A. How many times? So at this B, remember this represents that we've seen AB so far. So we would get the 2 here, so 2 plus 2, and then we get down here, which remember is ABC. So plus 1, so that's where we get the 5 for our first solution. Okay, so then we do AB. So for AB, we go here, so we start at the A. How many have we seen? 2. And then we get here, which is AB. There's 2 of those, so we've seen 4 here, right? And then we're gonna go BC. So we go BC, so how many times have we seen B? Twice. And how many times have we seen, this is representing BC here, so plus 1, so that's 3. So we have 3 for BC, and then B, obviously there's 2 of them, so we would just return 2. So that's essentially what you want to do. You want to build the trie. Every time you visit a node, basically in the trie, you're just going to increment its count by 1, and this will build the trie, and then we need a second pass through for every word just to count all of the counts here along that path until we get to basically the end of our current word. Sum those all up, and that represents the count of all the prefix sums. So relatively simple once you see that you actually want to use a trie here, but other than that, this question is relatively straightforward. So I think that we've explained it pretty well at this point. What I want to do now is actually go into the code editor where we will we unfortunately have to type up the code for our own trie, but once we do that, then the actual code for the problem is actually really trivial. So that's enough talking. Let's now go to the code editor and type this up. I promise it's really not that complicated. I'll see you there. We are back in the code editor. Let's type this up. Unfortunately, this is one of those questions where you actually have to define your own data structures here because there is no kind of built-in trie into Python. So we're gonna have to implement it ourselves. So remember that to implement a trie, you need trie nodes. So let's define the actual trie node first. So we're gonna say class trie node. And what this is gonna be is we're just gonna have a simple init function. And what we're gonna do here is we're going to say each node is gonna have some children and it is going to have a count, right? And this count is going to equal to 0. So what do we wanna do now? Well, we need to define the actual trie itself. So we're gonna say class trie node, and oops, sorry, class trie, my bad, we already defined the trie. We're gonna have an init function, so we define it, and obviously we're just gonna say self.trie is going to be a new trie node. And what do we wanna do? So we wanna implement our insert function because we need to insert things into the trie. So we're gonna define the insert function, and this is going to take in a word. So we're basically gonna insert the entire word into our trie here. And what are we gonna do? So we wanna get our current node, which is just self.trie because that's the root of our trie. And we're gonna say for char in our word, we're gonna say if the char is not in node.children, so basically if it's not one of the children of our trie, then what we wanna do is we actually wanna add it in there. So we're going to say node.children of that char is going to equal to the node. And what we're going to do now is we're going to move our kind of node up. So node now becomes the node.children for that character. And then because obviously we want to move to the next one, right? So then we would insert the next node into the node that we just created into its children, because obviously that's how the trie works, right? And then what we want to do now is we want to increment the count for that that current node's count is going to increase by 1, because obviously now we have a count scene. So at the end, all we want to do is, that's it actually. So this is the insert function. This will go through all the characters in the word and build our trie, right? It's going to start, something like root, and then it's going to go, for the example, it's like A, and then B, and then C. So that's essentially what the trie is going to look like. So that is our insert function here. Now let's actually define the function that's actually going to get the count given a word. So def count. So here we're going to take, sorry, not count. We're going to take the word, and now we want to find the count of the word, which remember is just traversing the trie and basically summing up all of the counts along the path for that word as we go character by character. So again, we're going to get the root of the trie, which is just self.trie here, and assign it to this variable node. And what we want to do is obviously we want to have a count variable to basically store the count. And what we want to do is basically the same that we did when we were actually parsing the trie, except this time instead of actually inserting nodes, we just want to take those counts. So we're going to say for char in word. What we're going to do now is we're going to add to our answer, so our count here, we're going to add to it whatever node.children of that character.count is. So node.children of char, so this should be char, apologies. These should be char as well, getting lazy here. We are essentially going to be getting, the trie node, getting its count, and then adding it to our count, right? So we're just visiting it and basically getting the count. And then the next thing we want to do is just move to the next node in the trie, which is obviously going to be the next character. So node.children of char. Okay, cool. So that is the count function. Last thing we need to do is simply return our count here, and we are done. So this is the hard part of the question. We've implemented our trie node. We've implemented our trie. Now all we need to do is actually solve the question itself. So let's go back into kind of the main solution class that we have here from Leetcode. And the first thing we want to do is actually just create an empty trie. And then we're going to say for word in words, what we want to do is we want to say trie.insert. So we're going to insert each of the words into our trie. And now what we want to do is simply return trie.count. So we're going to count for each of the words. So we're going to say trie.count for word on word for word in words. So like I said, the first pass through is to actually create the trie and insert all the words. The second pass through will basically just be getting the count for each of the words. So let us make sure we haven't made any stupid syntax mistakes. And node, okay, whoops. This should be trie node. Sorry, I did it with node before, but I realized that might be a little bit cleaner to call it a trie node. Let's now run this. Okay, it looks like it's being accepted. And if I remember, this one did take a little bit of time to actually get the okay, cool. So accepted. Nice. So we are good. Now, the only thing left is for us to actually talk about the time and space complexity. So let's think about what that might be. We solved the problem. It was accepted. Let's now think about the time and space complexity. So we basically have two functions here, insert and count. And they're actually going to have the same time complexity because they run on the exact same code, right? Inserting it is going to be going character by character, and count is just going to be going over the same characters a second time. So since they happen serially, we can just figure out what the time complexity here is. So there are n words, right? So for each of the words, we need to basically insert them into the trie. So if there's n words, and each word, let's just say in the worst case, is going to be of length k, then this implies that our time complexity is going to be big O of n times k. So this is for the insertion part, plus big O of n times k, which obviously is 2 times big O of n times k, but we don't care about constants when we talk about asymptotic time complexity. So it's just going to be big O of n times k, where n equals to number of words, k equals length of longest word. And so this is the time complexity. And for the space complexity, it's actually going to be the same thing. So in the worst case, every single word, so we have still n words, and let's just say that they are, of length k, and somehow all of those k letters are actually unique. So that way we would have all unique paths here. It's just going to be whatever the longest word is basically the amount of space we need. So let's just say it's big O of n times k on the space as well, because it depends on the number of the words and then the length of the words. So that is your time and space complexity here. Like I said, this problem, not too complicated. I think once you realize that you need to try, that part is simple, and then just kind of figuring out how to traverse it to get the count. But it's pretty straightforward because you just go straight down the try and count all of the prefixes. So definitely figuring out that you need to try is the key here. But once you do that, this problem is really simple. As you can see, the code is like super basic, and this is just your standard try here. Anyway, that's enough blabbing. Hopefully you enjoyed the video. If you did, please leave a like and a comment. It helps me tremendously with the YouTube algorithm. Seriously, you can just literally write algorithm in the comment section below, and that's totally fine. You don't even have to have some meaningful insight about how this problem changed your life, because I know this is the best YouTube channel ever, and my videos will change your life, obviously. Yeah, if you want to see more content like this, where I solve videos and make sarcastic jokes that no one will get because nobody really watches to the end, so I'm just blabbering to myself here, but whatever, then subscribe to the channel. You will have no shortage of sarcastic jokes and Leetcode questions. If you want to join a community where we basically chat about FAANG, getting in there, system design, Leetcode questions, you can have your resume reviewed by me, then join the Discord in the link below. And yeah, thank you so much for watching, and I'll see you in the next one. Bye.